You think you know what far away means. You have driven across a country and felt the hours compress into something abstract. You have looked at a map and traced your finger across an ocean and understood, in some rough way, that the distance is enormous. None of that has anything to do with where Voyager 2 is right now. Let's start with the number, because without the number, nothing else makes sense. As of this year, Voyager 2 is approximately 20 billion kilometers from Earth. Write that out. 20 billion kilometers. The distance light travels in roughly 18.5 hours. The distance a radio signal takes more than 18 hours to cross, even moving at the speed of light. When NASA sends a command to Voyager 2 today, they wait over a day and a half just for the signal to arrive. And that is not the remarkable part. The remarkable part is that we launched it in 1977, with technology that predates personal computers, with 8-track tapes still on store shelves, with a guidance computer less powerful than the device most people use to set a kitchen timer. That spacecraft is still out there, still transmitting, still sending back data. And it is about to do something that no object built by human hands has ever done before. There is a place where the sun stops, not where it gets dark, not where the temperature drops below something survivable. A specific, physical, measurable boundary, a transition zone where the sun's influence, its magnetic field, its constant outpouring of charged particles, finally runs out of momentum and stops pushing back against the rest of the galaxy. It is called the Heliopause. Think of the sun as constantly exhaling. Every second, it releases a stream of charged particles, protons, electrons, helium nuclei, in every direction at speeds between 400 and 800 kilometers per second. This is the solar wind. It doesn't stop at the planets. It doesn't stop at the asteroid belt, or at Saturn's rings, or at the orbital distance of Neptune. It continues outward, thinning, slowing, but continuing, for an enormous distance. At a certain point, something pushes back. The interstellar medium, the thin gas, dust, and magnetic field that fills the space between star systems, exerts its own pressure. And at the boundary, where the solar wind's outward pressure and the interstellar medium's inward pressure reach equilibrium, there is a transition. That transition is the heliopause, and it is not a metaphor. It is a real physical feature of space, as real as a shoreline. On one side, the sun's domain. On the other, interstellar space. The galaxy itself. No human-made object has crossed it. Until, that is, Voyager 1 crossed it in August 2012. And NASA confirmed in 2018 that Voyager 2 had crossed it as well. So the crossing has already happened. What comes next is something else entirely. Here is why Voyager 2 is the more scientifically important of the two spacecraft, even though Voyager 1 crossed the heliopause first and is farther from Earth. Voyager 2 still has a functioning plasma science instrument. Voyager 1's plasma science instrument failed in 1980, 3 years after launch, before the spacecraft ever reached interstellar space. That means when Voyager 1 crossed the heliopause, it could detect the change through other instruments, cosmic ray counts, magnetic field shifts, but it could not directly sample the plasma, the charged particle soup of interstellar space. Voyager 2 crossed the boundary with that instrument fully operational. And for the first time in human history, we had a machine directly sampling interstellar plasma, measuring temperature, density, flow, taking the actual readings of the medium between the stars. What it found surprised the scientists. The heliopause is thinner than models predicted. The transition from heliospheric plasma to interstellar plasma happened over a very short distance, far shorter than the fuzzy, gradual boundary that many theorists expected. The boundary is sharp, defined, almost abrupt. And the interstellar plasma on the other side is denser, hotter, and more pressurized than expected. Not hot in the human sense, still extraordinarily cold by earthly standards, but hotter than the models said it should be. Which means either the models were wrong or something is heating the interstellar medium that we have not accounted for. Both possibilities are significant. Both require explanation. Voyager 2 is the only instrument in that region of space capable of telling us which one it is. But there is a clock running on all of this. Voyager 2 is not powered by solar panels. At 20 billion kilometers from the Sun, solar energy is so diffuse that it delivers essentially nothing. Instead, both Voyagers are powered by radioisotope thermoelectric generators, RTGs, devices that convert the heat from the radioactive decay of plutonium-238 into electricity. When Voyager 2 launched in 1977, those RTGs produced approximately 470 watts of electrical power, enough to run a few household light bulbs. For a spacecraft, that is a meaningful budget. But plutonium-238 decays, and as it decays, it produces less heat, and less heat means less electricity. The RTGs lose approximately 4 watts of power per year. In 2024, Voyager 2's power output has dropped below 40 watts. NASA engineers have spent decades managing this decline. Heaters have been switched off, allowing parts of the spacecraft to cool toward the ambient temperature of interstellar space. 7 Kelvin, the temperature of the cosmic microwave background, the cooled remnant of the Big Bang itself. Non-essential systems have been powered down one by one. Science instruments have been rotated through operation schedules to distribute the dwindling wattage. In 2023, engineers discovered they had incorrectly included a power-draining component in their calculations, which caused the spacecraft to temporarily lose contact with Earth. For 5 weeks, Voyager 2 went silent. 5 weeks during which the most distant human-made object was unreachable. They recovered the signal. But the incident was a demonstration of how thin the margin has become. The estimates vary, but most of Voyager 2's remaining science instruments are expected to operate until somewhere between 2025 and 2030. After that, not enough power remains to run the heaters that keep the instruments within operating temperature. Systems will fail one by one. Transmission will eventually cease. After that, Voyager 2 will continue on its current trajectory, approximately 500 million kilometers per year, in silence, sending nothing back, receiving nothing. A dead piece of metal traveling through interstellar space at a speed that would cross the continental United States in about 10 seconds. Forever. Let's be precise about what forever means here. Voyager 2 is heading in the direction of the constellation Telescopium in the southern sky. In approximately 296 Zewi-Wenero years, it will pass within 4. 3 light-years of Ross, 248, a small red dwarf star in the constellation Andromeda. Not close enough to be captured by its gravity, not close enough to affect its trajectory in any meaningful way, just a nearby passage of 2 objects on independent trajectories. After that passage, Voyager 2 will continue into the Milky Way, into the enormous disk of 200 to 400 billion stars that constitutes our galaxy, moving at approximately 15 kilometers per second relative to the local standard of rest, the reference frame of the stars nearest our Sun. At that speed, it will take Voyager 2 roughly 225 million years to travel 1 light year. The Milky Way is 100 Zewen light years across. You can do that arithmetic yourself. The number it produces sits far outside the range of anything human language was built to express. There is no destination. There is no purpose to the trajectory beyond the physics of the initial launch angle and the gravity assists that shaped it. Jupiter and Saturn for Voyager 1, Jupiter, Saturn, Uranus, and Neptune for Voyager 2, which is the only spacecraft ever to have performed flybys of all 4 outer planets. It will not arrive anywhere. It will simply continue. decelerating slowly under the gravitational influence of the galaxy's mass, but never stopping. The interstellar medium offers almost no resistance, 1 atom per cubic centimeter, compared to the trillions of molecules per cubic centimeter of Earth's atmosphere. In the coldest environment in the known universe, friction is not a force. There is one more thing aboard Voyager 2. Attached to its exterior is a 12-inch gold-plated copper disc. Encoded on it, sounds and images selected to represent life on Earth. Greetings in 55 languages. Music: Bach, Beethoven, Chuck Berry, a Navajo night chant, Azerbaijani bagpipes, the sound of a pygmy girl's initiation song in Zaire. Natural sounds: thunder, wind, surf, a mother's first words to a newborn child. There is a stylus included, along with diagrams explaining how to play it. A message in the event, something finds it. The probability of that happening is effectively unmeasurable. The universe is so large and so empty that the odds of any object encountering Voyager 2 in any meaningful time frame are essentially zero. Carl Sagan, who chaired the committee that selected the record's contents, described it not as a communication strategy, but as a statement of intent. A message in a bottle thrown into a cosmic ocean, not because anyone expected it to be found, but because the act of throwing it mattered. The record will outlast the spacecraft's electronics by billions of years. The gold plating is expected to remain intact for more than 1 billion years of interstellar exposure, long after the transmitters fall silent, long after the final instrument fails, long after the plutonium has decayed below any useful output. The record remains, a circle of metal in the dark, carrying the sound of a child being born. NASA physicists studying Voyager 2's data are not doing so to tell a story about loneliness or human ambition. They are doing so because the data is irreplaceable. The heliosphere is not static. It breathes. It expands and contracts with the 11-year solar activity cycle. The pressure balance between the solar wind and the interstellar medium changes. And where the heliopause sits, its precise location, its thickness, its temperature profile, tells us something fundamental about how our star interacts with the galaxy it inhabits. There are currently no other spacecraft in interstellar space. The next mission capable of reaching the heliopause, if any is funded and launched in the near future, would take decades to get there. The data Voyager 2 is sending back right now, during these final operational years, has no substitute, no redundancy. When the signal stops, that window closes. And one of the deepest questions in heliospheric physics, how the interstellar magnetic field is oriented relative to the solar magnetic field at the boundary, and how that interaction shapes the overall structure of the heliosphere, is a question that only a functioning instrument in interstellar space can help answer. Voyager 2 is that instrument, the only one. The signal from Voyager 2 travels at the speed of light and still takes over 18 hours to reach Earth. By the time you hear about a discovery Voyager 2 makes today, the spacecraft will have already traveled another 9 million kilometers beyond the point where the measurement was taken. We are not watching Voyager 2 in real time. We are watching it as it was. The physics of distance makes every signal a message from the recent past, a postcard from somewhere unreachable by any other means. That will end. The power will run out. The signal will cease. And when it does, Voyager 2 will continue in exactly the direction it is already pointing, moving at exactly the speed it is already moving. Unaffected by the loss of its own voice, unaffected by whether anything is listening. The universe will not notice. The spacecraft will not notice. The trajectory requires no input, no power, no signal. The stars ahead of it do not know it is coming. They will not know when it arrives. It will simply go, as it has always gone since 1977, into the dark, beyond what we can reach, beyond what we can hear, beyond what we can follow. Forever. Thanks for watching. I'll see you in the next one.